So the Big Bang Theory, it states that the universe started as an infinitely dense and hot point.
Big Bang Theory.
Yeah. So this
infinitely dense.
And hot point. So the Big Bang Theory, in the Big Bang Theory, there are mainly two eras: the radiation era and the matter era. The radiation era and the matter era. And then under these eras, there are certain divisions, like they are named according to time and the events that happened during that time. So under those, there are epochs. You have to consider that there was no matter, there was no time, there was nothing.
There was no matter, no time, no nothing.
No nothing. Nothing existed.
So what was there?
That's what I'm talking about, the infinitely dense point. Epochs. There are also divisions under the eras. So the radiation era has the Planck epoch.
Planck epoch?
They're actually like 8. The Planck epoch, the grand unification, the inflationary epoch, the electroweak.
Grand unification.
Yes, the grand unification. The inflationary epoch, the electroweak, the quark epoch.
Electroweak? Then quark.
Yes, quark epoch, quark with an R.
What do you want to talk about today?
Today I want to talk about the Big Bang Theory.
Big Bang Theory?
Yes. Yes.
You get a new. Big Bang. What is Big Bang Theory?
The Big Bang Theory. This is there are many theories about the beginning of the universe.
The beginning of the universe?
Yes, but the Big Bang Theory is the one widely accepted one because it has a lot of evidence behind it.
Big Bang Theory.
Yes. So the Big Bang Theory it states that the universe started as an infinitely dense and hot point.
Infinitely dense?
Infinitely as in no? An infinitely dense point, it's like it was the universe. It started, you can consider it as a dot.
A dot?
Yes. And by the way, to understand this thing properly, you have to consider that there was no matter, there was no time, there was nothing.
There was no matter, no time, no nothing?
No nothing. Nothing existed.
So what was there?
That's what I'm talking about, the infinitely dense point. Actually, there wasn't even space. Yes.
So if there wasn't space, so what was there? If there is no space, then what is there?
That's also not yet discovered, but like there are no clear explanation. But that was 13.7 million years ago.
13?
Yes.
0.7
million years
ago.
Yes.
This world is 3 billion years old.
Yeah.
Isn't it? 3 billion years old. But this was 13.7 million years ago.
Yeah. So
how old were you then?
Of course I didn't exist.
Okay.
So the Big Bang Theory, it states that the universe started as an infinitely dense and hot point.
Big Bang Theory.
So this
infinitely dense
and hot point. So the Big Bang Theory, in the Big Bang Theory, there are mainly two eras: the radiation era and the matter era. The radiation era and the matter era. And then under these eras, there are certain divisions, like they are named according to time and the events that happened during that time. So under those, there are epochs. Epochs. There are also divisions under the eras. So the radiation era has the Planck epoch.
Planck epoch?
They're actually like 8. The Planck epoch, the grand unification, the inflationary epoch, the electroweak.
Grand unification?
Yes, the grand unification. The inflationary epoch, the electroweak, the quark epoch.
Electroweak? Then quark.
Yes, quark epoch. Quark with an R. The hadron and lepton epoch. So those are the epochs in the radiation era, because the radiation era became before the matter era. It's called the radiation era because at this point, when the universe had just expanded, there was a lot of radiation. So in order for matter to exist, for the matter era to begin, part of this radiation was consumed. Yeah, so
that to be consumed.
Yeah,
to allow the other one to exist.
Yeah, it's actually the radiation was converted into many forms, which the elements I'm about to talk about, in order for the matter to exist. That's why I told you that nothing existed at first. Yeah, so so the radiation era came under the Planck epoch. There still was no matter. There was a force.
13.7 years ago still. Million years ago.
Yeah.
That's the era we're talking about.
So in the Planck epoch, that's the first epoch of the radiation era. There was still no matter because when the universe was still at dense point, it was very, very hot, and it expanded because of the instability of itself. So as it expanded, the temperature started cooling. It started cooling, and it's even up to now it's still expanding. Yes.
Even now.
We are in an epoch called the stellar epoch. It's the one we are in right now. Yes. It's expanding. Yeah, it's under the matter era.
So what are the features that someone can say this is the evidence that it's expanding? How can you know that it's expanding?
That's what I'm going to talk about. Let me first explain it so that you understand the evidence when you already know. So, and I was talking about the Planck epoch, where there was no matter. There was no matter because the universe was very, very hot. So particles couldn't settle to form elements.
Matter.
Yeah, that's what I'm trying to mean.
I'm following.
Yes. So there was only the super force. The super force was the unity of gravity, the strong nuclear, the weak, it's also a force, and the electromagnetic. So that was the super force. And at the end of the Planck epoch, gravity split from these forces. Gravity became independent. So gravity is what it's contributing to the expansion, formation of galaxies, because gravity exists when there are bodies. So bodies but we're talking about huge bodies, because when we're talking space, we're talking huge things. So for example, the moon. Did you know that the moon plays a role in our orbit? For us to be in our orbit, the moon has a role it plays.
What is that?
If you try to move the moon, the earth gets off its orbit. Do you know why? Because of gravity, the gravitational force between the two bodies. Even the earth, if you move the earth, the moon will move.
So the two bodies here, you're meaning the earth and the moon?
Yes.
So the earth is a body?
Yes.
And the moon is a body?
Yeah, a planetary
And each
body.
of them play a gravitational role.
For them to keep in position.
If you disposition one of them,
yes,
the other one is affected as well.
Yes. That's how things are arranged in space. They are arranged according to their gravity afflictions, like the way they are. That's their logical thinking.
Positioning.
Yeah. So it will be a topic for another day. But black holes, they are the ones with the strongest gravitational pull in the universe. Gravity. Yes, they're called black holes. They are. I prefer to call them dead stars, something like that, because at first they were stars. Even stars have age.
Hey, yes. Stars we see.
Don't you see that stars have different colors? That's aging.
A star up there?
Yes.
It ages?
Yes. A star will start as blue, and then it will turn white, and then yellow, and then a supernova occurs. A supernova is that event where it explodes.
The stars, when they age out, they explode?
Yeah, they explode.
Hey.
Yes.
Yeah, so whenever I am seeing in the skies there a blue star,
that means that star has just been born.
it's just new,
Yes.
young, energetic,
But even
beautiful.
those ages, they are million years. These things happen in a very long time. So it's possible that there is no star has ever been born in your whole life.
My entire.
Yes, even the youngest star cannot be measured in our lifetime. For us, our life is very short.
Yeah.
Yes. So
You
that's
normally
what I'm
see blue
saying.
stars, white, very white,
Yes.
then
Yellow.
yellowish.
Yeah. Now the yellowish is because these stars have fuel, nuclear fusion.
Fuel?
Yeah, these stars are born within a cosmic cloud. I told you they are
A cosmic cloud.
Yeah, that cosmic dust in space. That is like, it's called the nuclear fusion reaction, where stars burn out their fuel. So as a star is born, there is more fuel than energy. But as it consumes the fuel and it grows, the fuel becomes less. Hence, the star's life, like, it's like saying,
reduces.
as you grow, one piece of bread won't be enough for you. So as the fuel runs out, even its light tends to, dim. And then eventually, because of
wears
gravity
out.
and other forces and other aspects, that's how it ends up exploding. But again, that explosion will spread cosmic dust, and that cycle will repeat again. Remember, I told you they're born from cosmic dust. Yeah, so the cycle will repeat. So in the radiation era, it ended when gravity split. And when gravity split and there was cosmic dust all over the place, it started rearranging the universe. That's when the formation of cosmic clouds came. And then remember, as the universe is expanding meanwhile. So as it's expanding, the temperature is cooling down. So there was room to form quarks. That's how the quark epoch comes along. So there was room to form quarks. Quarks are subatomic particles that combine to form protons and neutrons. So, and for after the Planck epoch, there was the grand unification epoch. And for this one, the super force was still there, but without gravity. And it also ended when the strong nuclear split. So the strong nuclear force is the one that went and started the birth of stars and the galaxies. You get what I mean now? Now, if we are to make you understand this better, we have a planet. A planet is in a solar system. A solar system is in a galaxy. And then galaxies are the ones that make space as we know it. So for us, we are in the Milky Way galaxy, and our solar system, Milky Way galaxy.
Milky Way
Yes.
galaxy.
And our solar system is that we can say it's a spiral. You have ever seen that image? It's a spiral, and we're at one of the wings of that. So a solar
we are
system.
just at the wing.
Just know, our system of the Neptune, Mars, it's just a very, very small speck of space. If you look at
Last time you said it's like a grain of rice.
Yeah, that's how it is.
On a tray.
Yes, that's how it is. Like, there is a lot of things that we haven't explored yet. So when the strong nuclear split, there came the inflationary epoch. This was the.
So is this all still the Big Bang theory?
Yes, I'm explaining. Like, don't you see
Bang.
how things are evolving?
Yeah.
We're going to get to that part where you get like the current thing. So we reached the inflationary epoch. In the inflationary epoch, the universe rapidly grew from the size of an atom to the size of a grapefruit. Just know all the things I was talking about while they were happening. The universe was still. It had expanded, but it wasn't so big. So in the inflationary epoch, it expanded rapidly to the size of a grapefruit. And then came the electroweak epoch. This one is when the electromagnetic and weak force split from the super force. I want you to remember that at the beginning, there was only force, there was no matter. So as these forces split, the ones that caused particles to gather together and start forming elements which form atoms. Yeah. So as we go on, the quark epoch, that's where quarks came. I already talked about that. So, and the quarks, as the universe continued expanding, they cooled down and they combined to form protons and neutrons. That's also the quark epoch. So as we go on, we meet the hadron epoch.
The hadron epoch.
Yes, the hadron epoch. That's where the universe cooled enough to form the protons and neutrons. And then the lepton, those were the last of the radiation era. The lepton and nuclear epoch. The protons and neutrons now. Remember, the protons and neutrons were formed from combination of quarks. Now they also combined to form a nuclei, like a nucleus, but in plural they're called nuclei. So as they went on, we entered the matter era, because once a nucleus is formed, an atom will be formed, and as atoms combine, that's when they start making an element. So the
now
element,
this matter we enter into it, that is about which year?
So that was the birth of matter. That was around 300,000 years from the Big Bang. Yes.
From the Big Bang.
Yeah.
Remember, the Big Bang is 13.7 million.
Yeah, million years ago. So
300 years later.
Yeah, 300,000.
300,000 years later.
Yeah.
That's when
when the first element is formed.
Matter.
Yeah. No, matter is, it's a broad name.
Yes,
we're being specific.
One of the matters. You create one of the matters.
Yeah, that's when matter first existed.
The first matter to exist.
Yeah, it was helium.
Helium.
Yes. And helium, now this is chemistry. Helium has two atoms on its outer shell. That's the illustration of a helium nucleus. With protons and neutrons inside, then 2 electrons just out. So helium was the first element. Now evidence, the way you see how I've narrated it, now the first evident thing you can see that the Big Bang really existed. There is a lot of helium in space.
So this helium, let me say, like, if I wanted to say this is a star, you would see a star. So
yes.
Helium, is it visible? You see it, or?
And not really.
Not really.
Because helium, it's like it's an element. It's let me say, helium. Helium is, how can I say it? It's a very light element. It's very light. Yeah.
It cannot be seen.
So even these other things we see. Okay, now can you see carbon dioxide? You can't. But actually carbon dioxide is a combination. There is carbon and oxygen. So you can't see carbon. You can't see oxygen. That's what I'm saying. So helium
you can't see air.
So helium also combined as the cycle went on and hydrogen was created. And then and so on and so forth, there came other chemical elements. So the first evidence of the Big Bang theory is the presence, the light element abundance. It's called light element abundance in space. That's the first. And then the second one is called dark energy or matter. Dark matter. Do you know?
This is what you're talking about, the black hole.
No, not really. Black hole is different. Yeah.
Dark energy.
So the dark energy, it's called dark energy because it's just hypothetical. It has not been proven to exist. We just have it that it can't be detected. That's why it's called dark matter. And it's also it also contributes to one of the theories of how the universe will end eventually. Because
this universe will end at one point.
Yes.
When the universe ends, what comes after?
Maybe it's believed that it's a cycle and this wasn't the first Big Bang to happen.
This universe where we are will end?
Yes.
So when
they are, like I specifically have around 3. The Big Crunch, the Big Rip, and the Big Freeze. The Big Crunch is where, just know right now, it's like a war of forces. So the war of forces is between the dark matter and the forces that are trying to keep the universe intact. Dark matter is trying to spread the universe. So the big crunch is when the forces that are trying to keep us together win. And then dark matter is overwhelmed and the universe collapses back into an infinitely dense point. That's the big crunch.
Dense point.
Yeah, the way it started, yes. So the big rip is when dark matter wins. No.
Do you know which joke, guy?
And then for the big rip to better understand it is when you pull. So when you pull a rubber band, it has a certain point. It's called the elastic limit. And when it reaches that point, what happens?
It breaks.
Yeah.
And it hits you.
But now, since it's just the way you see that space is very, like it's extensive. So the big rip is when everything will be ripped to shreds, like to the very last atom, the very last subatomic particle. So
subatomic particle.
Like from everything, even helium, you get destroyed to the very, very, very beginning. So that's the big rip. And then thirdly is the big freeze, when these forces will just balance. And this is actually like the most probable one, because you can see that as the universe expands, it gets cooler and cooler. So what if we reach that point where it gets too cold? Because I told you that the stars burn out. The stars are our source of light. They are the source of heat. For example, the sun is also a star. So don't consider stars as we know them, the shining what. A star is, the sun is a star. So even the sun, it's said that it will burn out eventually. I told you it's white. You remember what I said about ages?
In the previous interview.
Yeah, the cycle, it's believed that it's also in a cycle. And when that nuclear fusion reaction, like the nuclear reaction that goes on within the sun, runs out of fuel, the sun will just...
The sun?
Yeah, the sun might just explode. Hence, a solar flare. A solar flare is when everything around the sun will burn, like from the explosion.
Solar flare.
From the explosion of the sun.
Right.
Yeah.
This we are talking about in how many millions of years? When we are long gone, or just
we shall be long
in the
gone.
near future?
No, it's not in the near future.
So there is a time when the sun will also wear out
run
and
out of fuel. Because as the sun burns its helium, it produces hydrogen. Hydrogen itself doesn't support burning, so the sun, it's like the sun is suffocating itself.
What makes a sun to be a star, and what gives her that sort of hotness?
we are going down.
So
At the table there.
So the sun is considered a star because just like many other stars, though they don't have names, the sun is also runs on nuclear fusion. That's the process that produces its energy. So within the sun, like inside the sun, helium, it has a lot of helium, and helium is like its fuel. So the sun keeps on, it's a cycle. The sun keeps on converting helium into hydrogen, and as this process goes on, it produces a lot of heat. Actually, the temperature of the sun is 5,500 degrees Celsius. And just to give you a rough estimate so that you can understand how tremendous it is, boiling water is just 100 degrees Celsius. So the sun is 551 times hotter than water.
Yeah?
Yes. The sun, its temperature.
Water.
Its temperature, water, boiling water.
Maximum boiling water is 100 degrees.
Yeah,
Celsius.
100 degrees Celsius. But the sun, it is 55,500 times. Yes, that's the temperature of the sun. So it's 555 times hotter than boiling water. So you can imagine that heat.
Imagine when you put your finger in water that has boiled 100 degrees.
You can.
Now, imetwale tano makumi tano bitano.
What happens? What if the sun slopes down to the earth? What can happen?
I think everything would be burned to shreds. Like just know everything would burn. That's it. But the heat comes from the nuclear reaction within the sun. Yeah, that's the point. And also stars, the normal stars we know, they are also as you see them, they are all around cosmic clouds in space. So those cosmic clouds have helium. Actually, helium is the one that causes the clouds. So for a star to be born, there will first be a cosmic cloud that denses up, and as these, I told you, gravity. So these things come together because of gravity. So as they come together and react, that's the nuclear reaction I'm talking about that will give birth to a star. And now, these amounts in clouds are finite. So as they run out, that's how a star comes to die. But the star is the one that burns it.
Let us end here. We shall continue from here next time.
Okay.
Ibintu bingi kati njagala next time tutandike Big Bang Theory. What is it?
The Big Bang Theory, I was just left with the evidence part.
How long can it take?
I can summarize like in 10 minutes or something like that, because I just have these two to explain, the last two.
You said you're left with what?
The cosmic background radiation and the redshift.
You note them down. We'll begin with them tomorrow.
Okay.
Because when you give these people a lot of information at a go, our people don't want to they will get lost. That's why I have to give them in bits.
Yes.
Begun-Alituha, a software engineer student, Victoria University. Carl, bye-bye.
You're welcome.